So prove from first principles that two permutations both of the same integer n are conjugate if and only if they have the same cycle type. Okay, let us understand the question first. So I guess this is a statement that we all know and understand. So let us understand. And can somebody please explain what? Okay, let me write out, and then I'll ask you to unmute and. So, for example, let us do some example. Let us take n equal to 5, right? And so in one of the notations for writing, there are many different notations for describing a permutation, and one of the lessons of this problem is to understand the uses of various different ways of expressing a permutation. But one of the standard ways is the cycle, disjoint cycle notation. So for example, if I take 2, 3, 5, 1, 4, right? That is one way of one permutation. I guess you understand what this means. 2 goes to 3, 3 goes to 5, 5 goes to 2, 1 goes to 4, 4 goes to 1. That is the meaning of this. And another one, let's say 1, 2, 5, 4, 3. Okay, I have written two permutations of 5, and they have the same cycle type, right? Why are they? So the thing is, if they are, since they are the same cycle type, the statement claims that they are conjugate, right? That is one statement. And secondly, they're converse. If two permutations are conjugate, then they must have the same cycle type. Okay, I guess we all know this statement. We are familiar with this. We sort of use it. But what is the proof? That is the question. How to prove this? So how to prove? That's the question. But let us look at this specific case first. Can somebody please tell me which permutation will conjugate this one to this one? So let's give this some names. So this is, let's call it sigma. Let's call this tau. So I want permutation what is another letter? Let's say, let's use an English letter, S, such that S sigma S inverse is equal to tau. This is what I want. Can somebody please give that permutation?
In first row, we have 2, 3, 5, 1, 4. And in second, 1, 2, 5, 4, 3. This is equal to 1 goes to 4, 2 goes to 1, 3 goes to 2.
This one.
This one
Sorry.
And this.
Sorry, I am not following what you're saying. 1 goes to 4 in this sigma, right?
No. From first line 2, 3, 5, 1, 4, sir. In second line 1, 2, 5, 4 this way.
Oh, so first line, what do you want to write?
2, 3, 5, 1, 4.
Okay.
In second line, 1, 2, 5, 4, 3.
Okay. So what do you mean by first line and second line?
Permutation 2 goes to 1,
Uh-huh.
and 3 goes to 2,
Uh-huh.
5 goes to 5,
Uh-huh.
1 goes to 4, 4 goes to 3.
Very good. Okay. Okay. So so this is okay. So here is one way of representing a permutation by a cycle type. So can we write this as a cycle type in cycle notation?
1 goes to 1, 2, 3.
1 goes to
1 goes to 4.
4.
1, 4, 3,
3,
2.
2.
Nothing. That's all.
Okay. Yeah. And you can, so
fixed.
you can either write the 5 or not write the 5. Okay. So this is the same thing as 1, 4, 3, 2. If you want, sometimes it is good to know that you can also write it like this. Right? Because sometimes you want to keep track of the ones. Right? So this is another way of writing it. Okay. These are very good. Okay. And why do you say that this takes this to this? So, right, very good. So this is another way of, we've already seen two ways of writing a permutation, right? One is this with this cycle notation. The other is this two-line notation. Right, where on top you have the integers from 1 to 5 listed in some order, and in the bottom you have the corresponding images. Okay, so this is also equal to, let's write it more traditionally, the top line is always 1, 2, 3, 4, 5. Okay, so can you tell me, madam, if the first row is 1, 2, 3, 4, 5, in that notation, what would this be?
1 goes to 4.
1 goes to 4, 2 goes to 1. I just write what is below which,
goes to
right?
2.
4 is 3 and below 5 is 5, which means 5. Is this correct?
Yes.
Okay, so this is called, you can call this two-line notation, but usually two-line notation is written this way. But this is a good way of writing it. There is nothing wrong with writing it this way, right? So, notation, no matter what, one thing we, as teachers, we should be aware is notation is not fixed in mathematics. You can use any notation that is convenient for the problem. And in fact, choosing appropriate notation is one of the ingenuities involved in solving a problem. Okay. Now, this is called two-line notation. There is also one-line notation. I don't know if you have come across this, but that is just simple. What you do is, in one line, you just write the bottom line, where the first line 1, 2, 3, 4, 5 is understood. Okay, so this is called one line notation. So we have seen three different notations for permutations here. One is this cycle notation, then this two-line notation, and this one-line notation. Is this clear? Okay. Now the claim is, let's call this S. Okay, let's call this S. This, which is the same thing as this, which is the same thing as this. Right? Whether you write it like, or even equal to this. Whether you write it like this, or like this, or like this, or like this, it doesn't matter. It represents the same permutation. And the claim is that S sigma S inverse is equal to tau. How do I see this? How do we see this?
So better we act to 1 at both sides.
Okay.
We need a permutation, yes. Suppose exists. Therefore, satisfy the condition S sigma S inverse equal to tau, acting at 1 at both sides. That is, two functions are equal at any point.
Yeah. Okay.
Therefore, S sigma S inverse at 1 equal to tau of 1.
Okay.
But S sigma S inverse is same as acting at 1 is nothing but sigma of 1.
S sigma S inverse of 1. Okay, you're doing
at 1.
Sorry. S sigma
S
inverse of
at 1, acting at 1 at the point 1
is
nothing but sigma of 1.
Why?
So actually, suppose since sigma is a product of design permutation.
Yeah.
So S sigma S inverse is nothing but sigma of, suppose we call sigma as A1, A2, etc. some AK and so on. And this is nothing but sigma of A1, sorry, S of A1.
Mm-hmm. What do you mean? Sorry, Annamalai, I'm not following.
Okay, suppose in general, suppose you write sigma equal to A1 one way notation, A1, A2.
Okay.
Some
one line notation. Okay.
AK and into some another permutation. Suppose product of design permutation. Sigma equal to this into.
So sigma is this
right
much.
in one more permutation.
No.
Product of two permutation. No.
Permutation. What
Sigma is a product of two permutation.
Sigma is a product of two permutations.
Design permutation.
Okay.
Okay. So sigma equal to open bracket A1, A2, etc. AN, comma some B1, B2, BK.
Oh, like this you want to write. Okay. Sorry, like this you want to write.
Yeah. B1, B2 to some BK.
Okay. So in cycle notation, online
notation.
Cycle notation. Okay.
If sigma
this is not n, therefore.
Yeah,
let's not use n. Use n. Let's just leave it blank.
AK, AL.
Something. Okay.
Okay. Then S sigma S inverse is nothing but S of A1, comma S of A2.
Okay. This. Okay. So
acting at A1.
Okay. So is nothing but S of A1
comma S of, goes to S of A2.
S of A2.
And so on.
Okay. So this is a very important observation. Thank you. What you're saying, very good. Yeah, this is correct. Okay. And in fact, that's what I think she's using to give me what goes from S to tau, right? Sigma to tau, right? Because you send 2 to 1, 3 to 2, 5 to 5, 1 to 4, 4 to 3, right? So, observe. So let's use this sigma. So how do you write this now? So let me write out what Annamalai is saying. So if sigma is equal to A1, A2, etc., B1, B2, etc., and so on, other cycles, right? C1, C2, and so on. Right? Maybe and then S sigma S inverse, wherever S takes A1 to S of A2 ... S of B1 S of B2 ... and then S of C1 S of C2 ... etc. Okay, so indeed this is a very useful thing to keep in mind. Okay, this is not so hard to, once you've seen it, it's not so hard to remember. And why is this? The question is why is this? This is because you can because if you can prove this. For example, here is how to prove this. For example, let's take S sigma S inverse acting on S of A1, right? Where does this go? This goes to S inverse of S. So what is this?
S sigma of A1.
S sigma of A1.
But sigma of A1 is nothing but A2.
S sigma of A1 is nothing but A2. So it's S of A2. Okay. So this is a very good observation and it's easy to prove. Okay. And therefore, this problem is one part of this is solved, right? If I am given two cycles, let them be A1, A2, B1, B1, B2, B2, and so on. So the solution is, here is the solution. So if you write sigma is equal to A1, A2, so we are given that they are of the same type, same cycle type. So I'm doing that direction of the statement. Given that they are of the same cycle type, we want to show that they are conjugate. And for that, you write like this. So write out the cycle type, rather sigma in this cycle notation, and tau. What I know about tau is that it has the same cycle type as sigma. So I can write with some A1 prime, A2 prime, etc., B1 prime, B2 prime, etc., C1 prime, C2 prime, etc. I can arrange the cycles so that this cycle is the same length as this cycle, so I can call them A1 prime, A2 prime. So it's understood that this cycle has the same length as this cycle, and so on, right? Okay. Now, the S, or actually, I shouldn't say the S, because there may be very many different S's. An S that takes such that an S such that S sigma S inverse is equal to tau is given by, okay, now it is maybe not good to use cycle notation for S, but rather two-line notation. In two-line notation, as that was precisely what was given as the solution. So you write A1, A2, A3, ... and then B1, B2, etc., C1, C2, etc., in order, and below that write A1 prime, A2 prime, A3 prime. So while sigma and tau are expressed in cycle notation, this S is described in two-line notation. Okay. So then by this argument here, this proves that sigma and tau are conjugate. Because if I choose S like this, where S is described in two-line notation like this, then indeed S sigma S inverse is equal to tau, as is easily checked. And we have done this. Okay. So is this okay?
Yes, sir.
And if any questions, please unmute and express yourself. Otherwise, I am lost. I'm lost as to whether you are we are understanding. Is it clear or not? So, are there any doubts? Hello?
No, sir.
No? Okay. Somebody other than Annamalai, because he was the one who gave the solution, at least part of it. There was also another person who, I don't know the name, the lady who gave this permutation, who also had the same idea. Hello? Is this okay? Or do you want, should we go over this again?
It's clear, sir.
It's clear. Okay, good. Okay, thank you. Thank you. See, I need feedback. Otherwise, the problem with this digital way of doing things is that without feedback, I am lost. I am not in front of you, so I cannot see your faces. I cannot make out whether what I'm saying is getting across or not. So I need this feedback. Please do provide it. Okay. So how about the converse? If so, S sigma converse. So let's write converse. S sigma S inverse has the same cycle type as sigma. This is what we have to show, right? But then that is also clear, because if, so this is if S is given, so once again, let's write, this is also clear. Let me not, I will explain this in words, and I want you to understand. Okay. So let us take, so I suppose sigma is given here, right? It has this cycle notation. Right? And S I express in two-line notation like this. Right? And here is the trick. So think of S in two-line notation, but sigma in cycle notation or whichever notation. But the important thing is to think of S in two-line notation. Okay. So, or S as an explicit bijection. So you're not worrying about the cycle structure of S, right? You are thinking of it as a bijection as a map from S to, I mean, everything is a map from 1 through N to 1 through N, true. But it's just a matter of looking at it in a particular way. Okay. So if S takes A1 to A1 prime, A2 to A2 prime, and so on, B1 to B1 prime, B2 to B2 prime. And then we have observed in that case, by what Annamalai has said, this is S of sigma S inverse is nothing but S of A1, S of A2. I'm just repeating what Annamalai said. That's all. S of B1, S of B2, etc. So clearly, S sigma S inverse and sigma have the same cycle type. Okay, is this so? This finishes the problem. Can we move on, please? Or if there are questions, I can answer. This is a very important fact, and facility with this is will be very important for understanding any amount, even a little bit of group theory, because permutations form the most important example of groups. Basic and most important. Yeah. Okay, since there is no feedback, I assume you're all right. And then let's go to this. I want to suggest the following problem. Okay, so here is the problem. Number 2 that we are discussing. Okay, so I have R2 here. It's expressed in words in the tutorial sheet, but here it is in. So I have one line L, let's say, and another line K. Okay, so L and K represent two lines in R2 passing through the origin. Right. Okay, if I take the reflection in L, the reflection in L makes sense, right? If I have a point here, you drop the perpendicular from that to L and extend it on the other side, and this will be the reflection. So think of this as a plane mirror in physics language, and which is two-sided mirror. So everything here on one side of L goes to the other side, gets reflected to the other side. Points on L remain where they are. Okay, so so let's call this reflection in L. Let me call it L. I've called it R in the notes in the tutorial sheet. I'll change it to L because L, small l and capital L, that's the good correspondence. So reflection in K, let's call it K. Question is, can you describe geometrically K, so K of L, let's say. This is the problem. So let us discuss this problem. I want you to think about it and right now and give an answer, and we can discuss. Any thoughts?
If K equal to L, suppose both are same line, then we get identity.
Very good. The same. Okay, so at least one case. So if K is equal to L, then L equal to K, and K of L is K of K or L of L, however you want to write it, equals identity. Very good. Because you do a reflection and then do it again and you go back to where you were, right? Okay, good. At least in that case. So any other case. So what Anamala is trying to do is very good. So if a problem seems very hard, then it is good to try and simplify the problem or do special cases of the problem. There's nothing wrong with this. So you should not say, this is only a special case. We want to solve the general case. If you always keep thinking of the general case, then it may not be possible to unless you have an idea, of course. In any case, whether or not you have ideas, it is good to think of special cases. This is something that I don't often see people do it in as teachers, as students. We don't do it often enough. So I encourage you to think of special cases. Or there is nothing wrong with specializing. In this special case, how does it look? And what is often such analysis will, after a few minutes, you will see that you have gained a lot of insight and maybe enough insight to solve the general problem. Anyway, so that's good. So if L equal to K, in that case, we have a description. Yes. Any other special case you want to try?
So angle between K and L is 90 degrees.
Very good. So let's say angle between K and L and 90 degrees. So anything else you want to simplify anomaly? Okay, that's a good case. Yeah. Anything else you want to say? See, let me suggest it. So rather than think of, L and K are two arbitrary lines, right? Given to me. So I might as well assume that L is x-axis. I can turn my axis so that x-axis coincides with L. Nothing wrong with that. Correct?
Yes.
Okay. So let's say without loss of generality, and the standard shorthand for that is WLOG, we may assume L to be the x-axis. Okay. Now let's do a normalized special case where L equals, okay, we are assuming L equals x-axis and he wants 90-degree angle, right? Okay. So K is equal to y-axis. So the question becomes, if I reflect in the x-axis first and then in the y-axis, what is the resulting action or on R2? That's the question. Correct. Very good. Any ideas?
Negative of L.
What do you mean by that?
Suppose if you take arbitrary point in the first quadrant.
Okay, arbitrary point in the first quadrant. Okay, you want to call that x comma y?
Yeah.
Okay, where does it go?
So the reflection first you have to act in L is
It
x comma minus y.
degree.
Yeah,
x comma minus y.
Okay, there are two answers. Both are, I think, both are okay. So one by one. Yes, the other answer is also good. So xy goes to anomaly. Please say it.
X comma minus y.
X comma minus y. Right. Okay. And then now this
If
is acting L,
L,
right?
Yeah, capital.
Okay. And this is acting K. Where does that take me?
Reflection on y-axis.
Yeah.
It should be minus x comma minus y.
Minus x comma minus y. Because the x-axis, reflection the x-axis is nothing but changing the y coordinate from y to minus y. If I have something here xy, it goes here, right? If this is x comma y, this goes to x comma minus y. And that is true even if it is not just in the first quadrant, but any quadrant, okay? And similarly, k changes the sign of x. That's all it does. So this is xy going to minus x minus y. Okay, very good. This is a description in coordinates. But there was a second description which was more geometric. Both are good. This is good, using coordinates. But go ahead, madam. You had a suggestion. You had an idea.
So when we reflect about the x-axis, it 190. That is reflect of like this, but in geometrical way.
So the question is, geometrically, what is this transformation? Xy going to minus x minus y. How would you describe it geometrically? I heard an answer which was good. Which I know somebody said 180 degrees something. So if I have xy here, minus x minus y will be here, right? So what's happening?
So rotation about 180 degree.
After
Clockwise direction.
Rotation by 180 degrees. Yeah. Okay. And anomaly is saying clockwise. But what if I do anti-clockwise?
But our question is the composition is K composition L, not L composition K.
Doesn't matter. Let's answer this question. L and K are fixed. First I do x-axis and then y-axis. So reflection by 180 degrees clockwise. Note that 180 degrees clockwise is the same thing as 180 degrees anti-clockwise. So it doesn't matter in this case, right? Because generally rotation by theta clockwise is what rotation anti-clockwise? Rotation by, if I turn something anti-clockwise, clockwise by theta, to undo that, what should I do? Rotation by theta anti-clockwise, right? Sorry, what am I saying? Minus theta, so 360, sorry. I made a mistake. So this is
360
minus theta anti-clockwise, or 360 minus theta anti-clockwise. Both are the same, right? So for 180, clockwise or anti-clockwise doesn't matter. Okay, good. So we have a description in this particular case. Okay. But suppose we want to do this in general. So the one thing that we have learned from our special case is that I put L equal to x-axis. Nothing wrong with that. So let us formulate the problem like this. So here is R2. This is L. And K is some line like this. Okay, now I want to understand L first and then K. So this is what we want. So L and K, capital L and K, denote the reflections in the lines small l and small k respectively. So any thoughts?
An orthogonal matrix.
Yeah, it is an orthogonal matrix, surely. Why? So, okay, of course, we have to understand recall what orthogonal, etc. means. But surely this is an orthogonal matrix because it's a linear transformation and it preserves distances. Right? It's a linear transformation because reflection is a linear transformation which preserves distances. So once I do L and then K, both preserve distance, both preserve linearity. So both they are linear transformations which preserve distances. Therefore, it's represented by an orthogonal matrix. Indeed, that's a good way of thinking about it. So you may want to think, can you describe this as a reflection in something, or is it not correct? What does the previous example tell you? So if you think of it as a matrix, what is determinant of L? Or let us write out L as a matrix, right? Sorry. So let's write out L as a matrix. So before, I mean, this makes sense only if I think of L as a matrix. So how do I write it as a matrix? So let's do some linear algebra. Given a linear transformation, how do I express the transformation in terms of a matrix?
We have to find work for standard basis.
Yeah, look at standard basis. So I have, that's one way of doing it. In fact, you can choose any basis you want, but let's choose standard basis E1 0 and sorry
1 comma
0. I meant E1 is equal to 1 comma 0. So let's say E1 is here, which is 1 comma 0. E2 is here, which is 0 comma 1. And how do I write this matrix? Where does 1 comma 0 go to in terms of once I reflect in the x-axis? What is the image of E1 of this point when I reflect it in the x-axis? Same thing. So what should I write as the first column?
1 0.
1 0. Very good. Right. So remember that the first column is the x and y coordinates of the image of E1. Right. Okay. What E2?
0 minus
0 comma minus 1.
Of L this by writing So that, want to do this, I can do this by just
product
of matrices. Very good. This is the idea. You can just write out the matrices and think of it as a product of matrices, right? Okay. So what is determinant of L here?
-1.
-1. What do you think the determinant of K will be?
One.
Why 1? Okay, how do you express K as a matrix? So to think of it as a determinant, you want to express it as a matrix, right?
Yes, sir.
How do you express it as a matrix? Of course, you may say, I want to express it in standard basis, and then you have to worry about this goes here, this goes here, right? We need to worry about that, right?
So determinant is -1.
Okay, so Annamalai is saying -1, but why do you say -1, Annamalai?
-1 is 0. Huh? The first column of the matrix K is -1, 0. First column of the matrix K.
Of the matrix K is
-1, 0.
Why? Why?
Because it's a reflection about the y-axis. The standard, if we take the standard.
No. Here K is any line.
Okay.
So K is any line. So K, sorry, my picture is not very good. I am scribbling. I hope you please bear with me. So this is the line K. Question is, you express K as a matrix. So the point to exploit here is that to determine, see, what we want to do here is express K also in standard basis, in the standard basis. Otherwise, if I express L in some basis and express K in some other basis, then their product will not be the matrix product. Okay. So in order to do product of matrices, I must express K also in the same basis as in which I have expressed L. Since I've expressed L in standard basis, and if I want to use this, then I want to express K also in terms of standard basis. However, for the case, if I ask only about determinant of K, I can express K in a basis that is convenient for K, right? So what is the convenient basis to choose for K? So for K, you can tilt your axis like this. You can tilt your axis like this and put 1, 0 here, and think of this as, or think of this as, let me call them different letters, F1 and F2 here, where this is a perpendicular line to K, right? And so let me express the matrix of K in this F1 and F2. So what will be the matrix of K? K as a matrix in the basis F1, F2 is, where does F1 go?
Same thing.
Same thing. So what is the expression of F1 as a linear combination of F1 and F2?
1 times F1.
1 times F1, 0 times F2. Right? Okay, where does F2 go? Minus F2.
Minus.
Right? And what is the expression for F2?
0 times F1 minus 1 times F2.
So indeed, it is the same matrix, but with respect to a different basis. So what is the determinant?
-1.
-1, because it does not depend on which basis I choose. Right? I can choose whichever basis. If I choose, suppose I choose it with E1, E2 basis, what is the relation between this matrix and that matrix? They will be in the basis will be what is the correct word here? Fill in the blanks. Will be dash to the above matrix, to the matrix.
Similar to.
Similar, very good. Or conjugate. Yeah, will be similar or conjugate, which is the same thing as conjugate. Okay, and therefore they'll have the same determinant. So determinant of any reflection is -1. And when what is the product of these two? What is the determinant of the product of these two?
1.
So determinant of K of L is determinant of K times determinant of L, which is -1 times 1, which is 1, right? So what it shows is that K compose L cannot be a reflection in a line, cannot be a reflection in a line, because any reflection in any line has determinant -1. Okay. Okay. So the question is, what is K of L? So now we have this idea here. I want you to finish it. Maybe we'll move on to some other problem for the remaining 5 or so minutes or 10 minutes. This is something I would like you to work out, and maybe we can discuss it next time. So product of so what you can do is use some trigonometry if you wish, express K. So what you need to do, here is what you here is the outline. I don't understand why this goes upside down. Okay. I'm always puzzled by this. Okay. So let me, yeah, it's on top of the 3rd page. So here is what you have to do. Express K also in standard basis. You cannot avoid this now, because see, just to find the determinant, I chose a convenient basis for K, right? But here, if I want to compute, what we want to do, remember, is compute this, right? Then compute K of L, and see what it is. So the point is, in order that this I am able to compute as a product of matrices, I must express both linear transformations with respect to the same basis. So I have to express K also in standard basis. L was 1, 0, 0, -1. Okay, and so you have to express this. Okay, and so here is a suggestion. So take this line K and assume that it is theta, right? This angle is theta. And then you work out what, by using some trigonometry, use some basic high school trigonometry. To express the matrix of K. Then multiply these two and see what you get, and then interpret K of L geometrically. This is what you need to do. Okay, that's one way of doing it. So here is an alternate way of solving the problem. Yes, is there a comment or a question?
Yes, we use cos theta, sin theta in first row, minus sin theta and cos theta in another row.
Yeah, I don't. Okay, you are giving me the solution to this?
Yes, sir.
Okay, very good. Why don't we discuss the solution next time so that others also have a chance to think about it?
Okay.
Is that okay?
Okay, sir.
Yeah, and then K of L you can compute and see what you get for K of L and then interpret it geometrically. Okay, so here is an alternative, I should say, alternative way of doing this is to think geometrically. entirely. So see what happens to 2 points. Say, look at what happens to this point. Look at what happens to some other point. Choose 2 convenient points and see what happens, and then guess geometrically what is going on, and then prove it also geometrically. This is another way of doing it. Okay. Okay. So this is a very good problem to try, and it's very basic for what we are going to do. The reason I am doing this is because we need to think about dihedral groups, and so that's the next question. So let me come to the next question. So conjugacy in dihedral groups. Uh-oh. Sorry, I'm having a slight technical issue.
Okay,
It'll come back. Just 1 minute.
Okay, yes.
Okay, can you see this? Oh no, of course I have to start sharing. I guess we are back. Are you able to see this?
Yes, sir.
Yes, sir.
Very good, very good. So another question in the tutorial sheet is about conjugacy in dihedral groups. Okay, so I hope all of you have some familiarity with dihedral groups. I think all of us do. So, so for example, take D4. Okay, so what do you think of this as? How do you think of D4? Any suggestions? You know, there are different descriptions of D4 given in various books. So all of them, various descriptions are always useful, because for some tasks, some jobs, thinking in a particular way is useful, and for some other jobs, thinking in a different way is useful. So it is important for us not to get stuck in any particular way of thinking, but rather use different ways of thinking and choose the way of thinking that is appropriate for the problem. Okay, but okay, coming back, let's say to D4. How many elements does this group have?
8 elements.
8 elements.
8 elements. Okay, and how do you think of them? What is your
Rotation and reflections of
8 regular polygon reflection.
Sorry, say that aloud, madam. I was not able to hear it.
8. That is a regular polygon of 8 sides you have to take.
Here I'm taking D4, so this is polygon of
8 vertex.
4 sides.
4 sides.
Yes.
Okay, I take the polygon, which is the square,
Yes.
right? Okay. In general, if it is D8, for example, then you have to take the octagon, regular octagon. Yes, indeed, that's correct. It's okay. And then what do I think? What are the elements?
Rotation.
Yeah. So, yeah, there are rotations and there are reflections, right?
Reflections.
What are the reflections? So let's write out rotations.
Diagonal.
Right, rotations by 0 degrees, which is the identity, 90 degrees, 180 degrees. I'm missing something, 270 degrees,
270.
right? Okay, and then reflections. And which are the two? What are the reflections?
Horizontal and vertical.
How many of them? There are eight elements, right?
Horizontal reflection.
Horizontal we are having
Diagonal.
And then diagonals.
diagonal.
All right. Reflections in horizontal, vertical, and diagonal lines. right? Of course, we understand what we mean. When I say horizontal line, I mean this line passing through the center of the square. When I say vertical, I mean this line passing through the center of the square, and the diagonal lines like this, right? So these are 8 elements. Okay. Now, suppose I take so let me tell you how the previous problem is useful. Suppose I take reflection in this diagonal, right? And then reflection in this diagonal and multiply them. So let's call this K and L as in the previous problem. What is L doing first and then doing K? These 8 elements form a group, right? Correct? Which means when I do one of these and then another, the result must be one of these elements. Is this clear? That's what it means. And we have seen that if these are 90-degree angle, this is 90-degree angle here. Therefore, when I do L and K, and if they are at 90 degrees, then we have seen that the result is rotating by 180 degrees. So this is just the 180-degree rotation. Doesn't matter whether it is all clockwise or anti-clockwise. And so here is a let me take L prime to be this, right? So then question is L prime of K. What is this? L prime composed with K. I'm doing first L prime and then K. That is precisely like the previous problem where this angle is 45 degrees. And this must also be a group element. Which one is it? And so I hope you understand the usefulness of this, the previous exercise. It helps to think geometrically about dihedral groups. In particular, the exercise is very, very useful and very, very basic. So the problem is describe conjugacy in dihedral groups geometrically. So what I want to ask is, for example, take this reflection L and take this reflection K. Are they conjugate to each other? That's the question. Are these conjugate to each other? Yeah, is L prime conjugate to K? For example, those are the kind of questions we want to answer. Are the questions clear? So the problem, once again, let me remember, is I have said discuss.
Both have same cycle length.
Pardon me? Both have?
Same cycle length.
See, there is you have to be careful here. That thing was for the permutation group.
Yes, sir.
This is for the dihedral group. Things work a little differently here, although you may be able to use those facts.
Yes.
So thinking of them as permutations. So you said cycles, and therefore I assume you're thinking of them as permutations first. That is a very good idea, but it will not give you. You have to be. It's a good idea. You can use it, but you have to be careful because these are how to say. This is not the permutation group, right?
Yes,
this
sir.
is D4. So,
Yes,
so it is a subgroup, if you want, of the permutation group. But therefore, you can use that idea. I'm not saying throw away that idea. That's a good idea.
Yes.
But I'm only saying that you need to be a little careful in using that idea. That's all. But it's For example,
that
try
result
to
will not
use that
work for
idea.
any subgroup. That is you are
Sorry?
saying, sir. Whatever the result we are seeing for ESN, that does not work for D4, you are saying. Yes.
So
For
here,
subgroups, it will not work.
well, see, surely if you think of this as a subgroup of S4,
Yes,
right?
sir. Yes, sir.
Right. You can think of it as a subgroup of S4. Then one thing you can surely say, if two elements here have different cycle types, then they can't be conjugate in D4 because they are not even conjugate in S4.
Yes.
You can say that. But they may have the same cycle type, which means there may be conjugate in S4, but that doesn't mean they are necessarily conjugate in D4.
In D4, yes, yes, yes.
Okay, you understand that?
Yes,
so
sir.
Your idea is excellent. It's a beautiful idea and very useful. I'm only saying you need to be just a little careful in using it. That's all.
Yes, sir.
I'm not saying throw away the idea. I'm saying use the idea by all means. I'm only saying just be a little careful. That's all. For example, your idea, for example, to say if two elements have different cycle types, right? They are not even conjugate in S4. So they cannot be conjugate in D4. For example, you can use that to, for example, see whether L prime and K and L prime and L are conjugate. Okay. So very good. So discuss what my problem is, discuss conjugacy in dihedral groups geometrically. That's the question. Or that's the tutorial problem, which is an open-ended problem. But one I hope that you will like and we can discuss and gain benefit out of. I think now, Dr. Gurusamy, I think we are out of time, aren't we?
Yes, sir.
Okay.
Okay,
So
sir.
maybe this is a good time to stop, but I can send these notes for what they are worth to you, and
Okay,
I can share them on the WhatsApp group, no problem.
Okay, sir.
And the next meeting is on Thursday, is that
Yes,
right?
sir. Yes, sir. Thursday.
And Professor Anirban is scheduled to lecture.
Okay, sir.
And Dr. Gurusamy will send out the links.
Okay,
right?
sir.
Okay, I'll stop sharing now.
Okay, sir.
Are there any questions or comments you want to make? I can stick around for a few minutes if people have questions to answer. Others who have other business, I understand we are over time, so please feel free to leave whoever wants. But if some of you want to stay back and discuss, I'm happy to do that also. Is that clear what I'm saying?
Yes, sir.
Yes, sir.
Okay, good. So I guess there are no, I think people have had their fill for the day, looks like. So should we call it a day, Gurusamy?
Okay,
Yes,
sir.
sir. Okay, sir.
Yeah.
Okay.
I'm happy to stick around, but looks like people have other things.
Today,
to,
Karthi
which is
Deepam,
fine.
sir.
Yeah, which is fine. Yeah, which is fine. So we meet again then on Thursday. I'll share my notes on the WhatsApp group.
Okay, sir.
Okay, sir.
Okay.
Thank you, sir.
Very good. Have a
Okay,
good
thank you, sir.
weekend and rest of it. And yeah, this is only Saturday, right?
Sunday, sir.
Sunday.
Oh, today is Sunday.
Sunday.
Today is
Okay.
Sunday. Okay. Yeah, today is Sunday. Okay, have the rest of it. Okay, I'll see you sometime. Okay, Anirban will be here on Thursday.
Okay,
Okay,
sir.
sir. Thank you, sir.
Bye.
Thank you, sir.
Yeah.
Thank you, sir. Sanat, sir.
Thank you, sir.
Thank you,
Thank
sir.
you all.
Okay. Thanks.
Thank you, sir.